Okay, so brightness of some stars vary regularly. These stars are called variable stars, Cepheid variables. So you see the luminosity will go up and down, up and down. That's star getting bright and dark and bright and dark at different periods of time. So a student just literally just stares at the star, find the period and mean luminosity, and repeats this same process for different stars. So maybe another star may have a period like this. Just faster. Okay, so usually they'll tell us some story about the experiment and then they'll give us an equation. Then we need to linearize the equation. So first, what are we plotting on the axis? You need to check log L against log T. Ooh, log is a special thing. So when you see log, first thing we need to do is take the log on both sides. So log both sides. By the way, when the people write LG, what they really mean is log 10 on the calculator. So sometimes a shortcut is just log, LG. So what does it mean to take log on both sides? You take log L, okay, and what's on the right side? SKTA. So just take the log of the whole thing. SKTA. First step, done. Okay. So we want to plot log L. L is already by itself, log L, that's great. But we have a problem with log T because you see the T is stuck inside the log. We need to separate it out. So there is a rule where if you have things multiplied together like this, S times K times T, you can separate them out in the log. So I'm going to take out the T. So I'm going to do log T to the power of A plus log SK. So if they are multiplied together, they become added together. So for example, log of AB can become log A plus log B. Now if they are divided, just a recap, log A over B, the rule is they will be separated out and it becomes minus log B. So keep these two log rules in mind, especially if you don't take maths and it's quite new to you. Okay, we're almost there. Almost there. We want the T. Well, we have a problem because the small a is stuck there. So there's another rule. If you have a power rule, okay, T to the power of A, you can take it out of the log bracket and it becomes like this. So log L equals to A comes out and it's just log T plus log SK. There we go. And we have our straight line equation. Y-axis, they told us, is log L. X-axis is log T. And then y-intercept, y equals mx plus c, right? So mx plus c. So that means this sk is your y-intercept. Gradient here is A. So all you need to do is right here, gradient is A, y-intercept is log of sk. That's it. So practice linearizing. Straight line equation is your best friend. Okay, let's go on. Oh, here, so then you come to a table. We need to calculate some values here. What do we need to do? Calculate and record values of log T and log L. Include the uncertainties in which one? I'm gonna highlight this. Absolute uncertainties in log L. Okay, sometimes the uncertainties make us cry. So we're gonna practice calculating it. Okay, let's go. So log T. You know what? I'm gonna pull up the calculator on my screen. Show you some examples. Please say you know how to use a calculator, because it's very sad if you do not know how to use a calculator. Okay, let me clear my calc. Alright, here we go. So we have log T. I'll show you a sample. So this is in days. When you take the log, it means the unit of the value is in days. No. So how to do log? Usually you can just hit the log and then 22. This one's pretty straightforward. Question though, how much SF, how much DP? How do we know how much to write there? There is, let me warn you, a special rule for log. Just log. if you haven't seen it yet, go check out the video on how to calculate uncertainties and the decimal place for log. There's a video just for it. So special rule for log is, see, is 1.34, right? I'm going to write it as 1.34. Why though? The answer is because special rule for log is my calculated value, the decimal place, must follow the raw value's significant figure. What does that mean? So see this 22 here? This is two significant figures. Which means when I use this 22 to calculate 1.34, it must have 2 or 3 decimal place. Notice the change from SF to DP. Usually we do SF follow SF, but in this case it's DP follow SF. So be careful of the extra little detail there. So I'm going to shortcut a bit. You can pause the video if you have not calculated. But I'm going to calculate everything because I've already calculated everything just now. So I'm going to write it down. So the rest should be 1.51, 1.62, 1.73, 1.89, and 1.99. Side note, if you want to do 3 DP, is that allowed? Yeah, you could do 2 or 1 extra. So, or 3 decimal place. But usually, if it's not necessary in the graph, I really am lazy to plot it out because this is log t, right? Let's go check the graph. What's the smallest of log t? Okay, log t here is our x-axis. So what does one tiny box give us? Usually I recommend you write this down. One tiny box is this small thing, this tiny little. Okay, let's check. 1.3 0.01. So one tiny box is 0.01. So if I have a value like, 1.342, it's pretty useless to have the extra 2 there because I need to round it off anyway. So might as well, I don't need to include the 2, I just 1.34. Because my graph here only can do 0.01 precision in the small boxes, so nah. 1.34 is pretty fine for this graph. We want it to be an easy job later. So I'm going to stick with 2 decimal place 1.34. Yeah, no need 3 decimal place lah. Okay, log L 10 to the power of 30. How do we do this? Well, you see, the unit here, 10 to the power of 30 is already there. So literally, you just press calculator, log off, just take 2.9 inside there. That already takes into account the 10 to the power of 30. Okay, so we do the same thing here and check your decimal place very carefully. Here we have 2SF. So my value when I write it out can also be 2 dp. So 0.46 for example. So it can be 2 dp. 2 or 3 dp. But once again, check the graph. Let's write down on the graph. What's the smallest one box? So here one box is 0.01. Yeah, 0.01. It's only a 2 dp precision. So I wouldn't recommend going to 3 dp because there'll just be a lot of extra numbers to deal with later. Okay, so let's write it all out. You can pause the video again if you haven't calculated it. I have calculated it, so I'm going to write my values out. 0.69, 0.84. You can see you get the same numbers or not? 1.20. Ooh, here is 2 dp. Correct, Okay, correct. 1.32. 2SF to 2 dp. Okay. Now here comes the part where we have to calculate the uncertainty of what's highlighted there? Log L. How do we calculate the uncertainty of log? There's 2 ways. There is a video talking on just how the 2 methods, how to calculate. You can go check that out. Or I'm going to do a crash course right now. So, method 1, if you forget, your go-to method is to take half the range. Half the range. That's method 1. You can apply it for any uncertainty. Log, normal numbers. But let's see, what does it mean to take half the range? Okay, I'm going to write it up here. So method 1. You want to find the absolute uncertainty in log L. What you need to do is half the range. So what is the range? Largest minus smallest. So you need to take log of the largest L minus log of the smallest L. Okay, you can press it in the calculator, or a different format of writing this if you want to combine it is half of log. Remember just now we can combine log values when they're minus. This is the one of the identity, L max over L min. This looks nicer, easier to press. Okay, what's the example of L max and L min? Let's look at the case example for the first one. So L max, what is L? L is our 2.9 here, right? Plus minus 0.2. So in this case, let's use pink. Here, your largest possible value of L is 2.9 plus 0.2. So 0.2, so this will be 3.1. The smallest possible number here will be 2.9 minus 0.2, so that will be 2.7. So if you wanted to calculate a sample, first one will be half, press log, then take the maximum 3.1 over 2.7, and that's it. You get your value. Okay, let me try to press the real calculator. Half times. If your calculator doesn't have log, please remember that LG represents log 10 if you need to type in the base. Okay, some calculators just cannot include both. 3.1, 2.7, 0.02999999. So how do we write the SF and DP? Rule of thumb is try to follow the DP of the value. So this one is 2 DP, right? So I'll try to do a 2 DP as well. So 0.03. Okay, that's one method. Another method I'm going to show you, you have to memorize a very special identity that is just for log and longs. So first method, half the range. Second method, I'll just write it here. Special identity. The identity goes like this. If you want to find the absolute uncertainty log L, you need to take 1 over ln of the base, which is ln 10, whatever base that is, times the uncertainty of L over L. An example calculation for the first one will be like this. So I can take example 1 over ln, since log is base 10, so I'll put 10, times uncertainty L is 0.2 over 2.9. Where did that come from? Here. 0.2 divided by 2.9. So this one you can use, but you need to memorize the formula for this. So times 0.2 over 2.9. Also 0.03. Okay, so they agree. So which method do you want to use? I suggest you know both if you want to, but you can stick to one if it's like too much to remember. Okay, so I'm going to go ahead and write out all the other error bars. You can pause the video if you have not calculated them and check if you got them correct. Okay, so this one should be 0.02, 0.01, 0.01, suddenly increase 0.05, and then back down to 0.04. It's a bit weird, but oh well. Okay, so there's 1 mark each for each of these values. And note, how do I know to choose how many DP for this thing? Well, the masking is very vague on this. They don't really say. But number 1, I would try to follow DP of what is needed in the box. When you plot on the box, okay, the graph just now only takes 2 dp. So then the value also takes 2 dp. So I follow the dp of your value. Try to follow. And number 2, check the graph's precision, or the graph's small box. Don't need to go any smaller than that. Don't need more decimals. Usually it's 1 SF, or there'll be one number here lah. So like 0.03, not 0.034. Usually like that's too many already. So go for the least. Don't need to do extra work. So check graph small box, because these values are for error bars. These are for error bars. Alright. Okay, let's continue running through. So if you get all these values, you should plot out something that looks like, I think I plot a sample here. Something like this. So what are error bars? In case you don't remember what those are, if you have a value, scan is not the greatest, but I'll zoom in as big as I can and I'll redraw it. So at a point, you need to put an X. Let's see, what color shall we use? Orange? Yeah, we got an X. Okay, then let's say you have a plus minus 0.03. Then you go up by 3, draw a line. Go down by 3, draw a line. That's it. Error bars. That's what you need to do. So do it for all your points. Make sure you have these vertical error bars. Sometimes they can be horizontal, sometimes they're vertical. You really need to check which axis is your uncertainty. Okay. So yeah, same rule applies for paper 3. The size of the X must not be bigger than one tiny box. You see this? That X is how small it should be. Your error bar should also not be too big. Okay, the length should be 2 boxes and go down 2 boxes down there as well. Okay, so that's it. Plot, 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 and you should get a best fit line. The nice thing is you can check your best fit line in the mark scheme. They will tell you the gates which your best fit line should pass between. So go and practice drawing your best fit lines. So what are gates? Something like this. So let's say I have a best fit line, and then these dots that I draw here and here, these are the values given by the mark scheme. If your best fit line passes between these gates, you know, you want to go through the door, right? Nah, these are gates. If you go through the door, good, your best fit line is a pass. So in this case, I don't know which one is the best fit line, but the best fit line is pass. Woohoo, it went through the gates. There's 2 gates. One gate here, at the bottom, they will give another gate. So you see, just nice. The line here passed through the gate. So check your best fit line. Mark it on your paper. Okay, worst fit line. Thing you need to be careful of is, when you plot worst fit line, it needs to be the steepest or shallowest possible. There's 2 possible worst fit lines you can draw. How do you know which one to draw? It's really up to you. So for example, give you a sample. Sample. This is a graph. These are your points. These are your points. These are your points. Okay, let's pretend these are our points. Worst fit number 1 can be the steepest possible. So I start from the lowest error bar down here, connect it to the highest error bar up there to make it as steep as I can. So let me see if I can do that. Ding. Okay, turn it to the top. And then connect to the bottom. Oh man, this one node just okay, he doesn't want to go in between. Oh, there we go. There we go. Okay. So this is called a steepest possible worst fit. Steepest. You make it steep by connecting to the top of the first error bar, or here, the bottom of the other error bar. Another possible bad worst fit line is to make it as shallow as you can. So the reverse is then, why don't you try connect the bottom here on top? Oh, can I get it to go there? to the top of the other line. Something like this. Let me see if I can make it long. Come on, come on. Okay, there we go. There we go. Okay, so this is another worst fit line called the shallowest worst fit line. So 2 possible answers. It's really up to you which one you want to do. This is the bottom. And now this one connect to the top. Don't need to draw both. Just choose one. Choose one. Choose one. Choose one worst fit line and draw it. Label it worst fit line. There is one danger though. One thing you must be careful is your worst fit line must pass through every single error bar. So let's say we have a troll here. This troll, what should I do with this troll? This troll point wants to be like this. Okay, we have a problem here now. Because you see the pink color line? It's not passing through the error bar. So how do we draw a shallowest worst fit? Now in cases like this, I will just recommend I'll just draw the steepest, don't draw the shallowest. Because you have a problem here. Or another thing you can do is adjust the shallowest worst fit so that it passes through the other point. So what I'll do is I'll probably just tilt this up a little bit. Like that. They say, but miss, it's not connected to the bottom anymore. It's okay. Shallowest possible. You must make sure you pass through the error bars. And then you see, oh, down here, maybe it doesn't pass anymore. Okay. Adjust. Okay, give me a second to adjust. There we go. Pass through the stem, the main stem of the error bar. Okay, so keep an eye on these two things. As steep as you can, make sure it passes through all the worst fit lines. Alright. So things to note out. Label, please. I need to know which line is which. Best fit, worst fit. If you don't label, you kind of lose all the marks for all those hard work. Last thing to do is gradient triangle. So whatever points you choose for your best fit and worst fit, draw that gradient triangle with dotted line. And if you can, label what points did you choose on the line. Can we see them here? Yeah. It helps you, it helps the examiner mark. Okay? And make sure gradient triangle, dotted line. Okay, that's all the comment on the graph. So once you get that, you need to find lots of gradients. I'll just go through my workings very quickly based on these points here. And then we'll look at the last part, which is a bit of a headache. How do you do with calculation with log? Alright, determine the y-intercept of line of best fit, include the absolute uncertainty in your answer. Can we just read the y-intercept of this graph? Let's check. Ooh, we cannot. Because look at this here, 1.3. That's not the origin. So this here is not the intercept. We cannot read from the graph. Reminder to self. Y-intercept is only visible at x equals 0. So if this is not 0, it's not the y-intercept. Next. So what now? Calculate. So sample calculation of points here. I'm going to do a sample. You can probably press calculator along with me if you want to. We got a straight line, right? Y equals mx plus c. So if I want to calculate my y-intercept, I just need to find a point to use my gradient. Oh, where's my gradient? Can we not calculate our gradient? Oops, we missed our gradient. Ah, here it is. So gradient, okay, sample calculation of my gradient. So I pick some points. What you need to do is calculate one for your best fit line. For example, you can write it out like this. So 1.21, 0.49, 1.9 minus 1.36. Note that there are no units. All these have no units. Log of values have no units. None. So this one, I should get about 0.72 or 0.54. Why do I write it like this? So I can check my SF later. So SF, this one is about 2 SF. Bottom also 2 SF. So I guess I'll follow 2 SF as well. Just for consistency. No units. Okay, you need to do one more for your worst fit. Worst fit here, 1.23, my points, 0.49 over 1.9 minus 1.38. So I have about 0.74 over 0.52. Okay, so it's about 1.4. Alright, so now when you want to find worst fit line, uncertainty with your worst fit line, remember there's one thing here you need to do, absolute uncertainty. So yes, we can write 1.3 already, but one more step is uncertainty in gradient. We cannot follow the standard half the range, right? But to find half the range, we need to do the steepest worst fit line minus the shallowest worst fit line. We didn't do that. We only did one worst fit line. So that is already half the range. So no need to half. This is one method. Or we just take, this one is absolute value. We just take the best fit line minus the worst fit line. No need to half. Because by doing the best, it's really worst. Okay, so best is like this. Worst, worst. So this is worst fit line number 1. Worst fit line number 2. Best fit line is already kind of like in the middle of both. Half the range. Okay, so just take 1.4 minus 1.3 gets 0.1. So make sure you write here 0.1. Right. So we have our gradient. Let's go. We need to calculate our intercept. Okay, so I'm going to pick a point using point from my graph. So here with my point, I'm going to write the point so we can see what we're doing. 1.90, 1.21. I'm going to calculate. Best fit is 1.21 minus 1.3 gradient 1.9. I should get negative 1.26. We need to do again for worst fit line. So this point is on the best fit line. Then you get a best intercept. So with a point on the worst fit line, I'm going to take 1.9, 1.23. This is on your worst fit line. This one is needed later for uncertainty, so let's just calculate it also. 1.23 minus gradient. So my worst fit gradient is 1.4. X value. I think that's it. Okay. Calculation negative 1.43. Okay. The reason for all these two intercept is for the absolute uncertainty in the answer. So our answer here, we can write negative 1.26, or I would prefer to round it off to 2SF. Yeah, I can do 2SF or 3SF, it really depends. Shall I keep? I'll keep the 1.26, fine. Okay, I'll keep the 1.26. And then to calculate the uncertainty in C, we do half the range, but when we have another problem. Half the range, we need the shallowest minus the steepest worst fit line. But I only drew one worst fit line, so usually we don't do this to save time. We just go with best minus worst. So take the best worst fit line minus the worst fit line. These are two methods. Okay, so I will go with this one. Because we only draw one worst fit line. No, we draw so many. Okay, so minus both 1.26, 1.43, I should get 0.17. So I can write here the uncertainty as 0.17. Or alternatively, I could do negative 1.3 plus minus 0.2. Also okay. Do we have units? No, we don't need units. Okay, continue. So that's the first part. They may ask you to calculate intercept. Then, determine the values of A and K. So somewhere in your equation earlier, there should be an A and a K. We need to use our gradient and intercept to find these two values. What is A and K? Okay, scroll all the way back. In the beginning, Gradient is A, intercept is log sk. I would suggest you take this, rewrite it down there. That's the first thing you should do. Just take it, just rewrite it down here. For example, gradient is A. So this right here, A equals to gradient. That's it. That's it. That's it? Yeah, that's it. Okay, A is gradient. So what's the gradient? 1.3. Done. So that's right here, 1.3. But not yet, not yet. We are not done. We need to calculate absolute uncertainties. Okay, the good thing is there's no units, so I need not to be concerned with units. So if A is gradient and the gradient is 1.3, they literally have the same uncertainty. So the uncertainty of A is exactly the uncertainty of my gradient, which is 0.1 just now. So I'm just going to copy that value down here. Very nice. I like this. Oh, the headache comes from the second one. Let's rewrite first. From the front, we have intercept equals to log sk. The y-intercept is log sk. Now you need to be very careful when dealing with logs. You need to check the axis. Check for a prefix that is hiding there. What do I mean by that? Okay, hang on a second. Let's go back up. So log sk is y-intercept. So it's some value on the y, right? Kind of like this. This will be a y-intercept here. Notice this. 10 to the 30 watts. That means when I take the log of some value, I get 1.3 for example, but there's this 10 to the 30 hiding inside the log. So I need to be very careful. I'm going to write this down. 10 to the 30 is hiding inside there. So I'll put a comment here. This log sk is times 10 to the 30. Hiding inside there. This is a unit. Okay, this is so-called the unit of it. So we need to undo the log. Okay, how do we undo the log? Log is base 10, right? So when you want to open up a log, because you want to take out the k value, because we want to find k down here, first you write is the base, 10. 10 to the power of y-intercept equals to, then you write the contents of the log. What's inside the log? sk, right? sk. Then we have a problem. What do you do with the 10 to the 30 that was hiding inside the log? You see, when we open up the log 10 to the power of y-intercept, actually we need to put the power on this side here. 10 to the 30 sk. So remember, 10 to the power of whatever the stuff is, and include the hidden prefix inside there also, because you will need it. Okay, let's find the k in the end. So k here will be 1 over s times this whole thing. 10 to the intercept times 10 to the 30. This is such an odd calculation. Gotta say. Okay, s. What's the value of s? Do I have an value for s yet? Oh, it's given. I was like, what's that? S is right here. Great. One less you need to worry about. 3.85 times 10 to the 26. 10 to the power of my intercept, which was negative 1.26. If you take negative 1.3, you might get a slightly different value. So it depends. Times 10 to the 30. So let's smash some calculator buttons. 10 to 26. So 10 to the power of negative 1.26 times 10 to the 30. So you can get somewhere 100 over, 120, 130, 140, depending on your decimal rounding. So here will be example 142.74. So I could write it as 140. plus minus. We are not done yet. So to find the uncertainty in log, I am going to, I don't know what, means to use the identity or what, how? Okay. Here, we are not finding a log value, we're finding the uncertainty in k. So when all else fails, there's only one method. That is to find the uncertainty in k. I'm just gonna go with half the range, you know. Half the best minus worst. Wait, half of the shallowest minus deepest. We don't have that. So we're gonna take just the k best minus the k worst. This is the same as what we did for gradient and intercept just now, remember? Okay, so we're gonna use k is calculated from the intercept, best fit intercept and worst fit intercept. So we're gonna follow the same thing here, best and worst intercept. Okay, so what was the equation for k again? Let's draw a box around it. This was what we did for k, right? So k best, let's go. I think I'm going to use a different color here. So uncertainty in k will be for best intercept 1 over s 10 minus the best intercept times 10 to the power 30. That's the first one. Actually 10 to the power 30 can factorize out. Okay, I'm going to factorize that out. Minus the worst intercept okay, and there's a times 10 to the power 30 which I factorized out. Woo, look at this. Monstrosity! Okay, let's plug in the values. So we have 1 over 3.85 times 10 to the 26. Best intercept, negative 1.26. Worst intercept, negative 1.43, I think. Let's double check. Yeah, 1.26, 1.43. Wow, this is a hard calculation. If you've never done this before, you're like, oh, miss, what is going on? Okay, take time to digest, okay? Times 10 to the 30. Oh, and finally, if you press calculator, everything should get about 46.24. I can kind of round that off to 50, maybe? Let's do 50. Okay, let's do 50. 50. Just keep the SF same. Since I round the other one to the 140, so I'll do 50. Rounded off to this placing. Okay, so that's to be careful of the uncertainty of a very scary number. If there's log involved, just half the range. Or in this case, not half the range, best minus worst. Best intercept, worst intercept. Okay, last part. So with all these calculations, you're going to use those values again, one last time. So here, a variable star has a period of, can you see the values here? Period of 50 days. Determine the luminosity of the star. So there is two methods. Method 1 is to go back all the way, up some more. Go back all the way to the original equation that you set up here. Log L, A log T, log SK. I'm going to rewrite this down there so we can see how to use this. This is usually the safer method. Okay, we were going to rewrite the whole... What are we going to rewrite? Oh, we're going to rewrite the whole equation. Okay, let's do that. So, earlier we linearized a log. So we just copy the thing, okay? Method 1. Log L equals to A log T plus log SK. Right? And we also recognize the gradient and intercept. A was gradient, SK was intercept, right? So the second thing you can do is we change it in terms of our graph. So this will be gradient times log T plus your intercept. This method is a bit safer because it depends on your intercept. Maybe just now the calculation up there messed up already, you got it wrong, it's okay. Gradient intercept, just write it down. So here's an example calculation. So L, determine the luminosity. Okay, never mind. It's right here, log L. My gradient was 1.3. Log T. T is 5 days. Period of 5 days. So I just write 5. Plus my intercept, which was negative 1.3 or 1.26. I'm just going to go with 1.3. Okay. I wonder what if I do 1.26. Let's try it. Never mind. Here in the log, when you do a lot of rounding, it does affect your values a bit. Never mind, we'll go with 1.3. Okay, so need to undo the log. We need to find what is L. But once again, remember, L has a hidden power inside there. Oh my goodness. So I'm going to write one more line here. Log L. If you check the table earlier, actually there is a times 10 to the 30 hidden there in watts. Okay, I'm just going to put a stroke here to show that that's the original unit of L. And then we have all these values here, which I'm going to combine into a digit. 0.391, blah, 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 blah. So when we open up the log, what do? L equals to 10 to the power of negative 0.391, blah, 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 times 10 to the 30. Okay, so let's press calculator for that. So 0.391. Oh, I forgot a negative sign. Whoops. My bad. You know, for log, actually these digits here, you might want to include that as well. So I'm going to try see if I can find the full digit. Okay. 39. Okay, let's write it down. 391.339. Let me include more digits a little safer, a little bit. Okay, then we go 10 to the power of negative 0.391339 times 10, 30. So this one is like 4.1 times 10 to the 29. Big values, big values. So yeah, we'll leave it as this. This is one method. Okay, so you start with the original equation that you did before. Another method, a slightly more risky method, but it may be a bit shorter sometimes, is to use the unlinearized formula. So unlinearized formula, you go all the way back to the top again. I don't want to scroll in case my computer hangs. Is L equals to SKTA. Remember, then we took the log and then only we get this linearized version. So if you don't want to take the log, you can use this method, but there is a danger to it. I'll show you in a bit. So L, we need to find L. Great, L is already there. Fantastic, I like it. S, the value of S is given, right? This S here. 3.85. Okay, let's just write the whole thing. 3.85 times 10 to the 26. K is found previously already. We could use the value. So 140. T is 5 days. And A is 1.3. That's it. Looks shorter, huh? Very nice, huh? Okay, let's press. 3.85 times 26 times 140 times 5 to the power of 1.3. So I get about 4.4 times 10 to the 29. Okay. It's a bit different from my first method, but that's okay because log, any rounding difference will make a big difference. So I'm just like, sure. If you want it more accurate, if you want both of these answers to agree, you just keep all the decimals throughout the whole thing. and you'll be okay. Okay, so about 4.1, 4.4, which one you choose, it really depends. There's no right answer. You just follow through your method and you'll be okay. So I'll go with 4.1. Looks nice and short. So I'll go with 4.1. So what are the pros and cons of both methods? Well, you see, this first method here doesn't depend on my calculation of A and K. See? Doesn't depend on calculated values A and K. Whereas on the right side, I have to be a bit careful because my A is from up here and my K is also from up here. So if I did not know how to do this part, or I did something wrong here and these values are wrong, chances are it may also be wrong here. The danger of method 1 though is you need to remember that your L has a hidden unit prefix kind of thing here. It's in the unit of 10 to the 30 watts. So L is 10 to the 30 watts if you check the table earlier. So there are pros and cons to both. I would encourage you, if you know how to do both, just do both methods and just compare the answers. If one of them is really off, then you know something's wrong. But only do that if you have time. Okay, so back to this L 10 to the 30. Go back to your table earlier. Can we go back? Come on, can we go back? So the graph here, see this? L is times 10 to the 30, so L values have this unit of watts and prefix hidden inside the log. But the log value itself, like 1.3, no unit. The unit is hidden, wrapped inside the log. Table here also you see it, L is 10 to the power of 30, hidden inside the 0.46. Haven't come out, hidden. Okay, so I think that's all for this paper. Question 2.